Very welcome to the presentation, Discrete Steps Towards Approximate Computing. A variety of authors have contributed. Myself, I'm in the middle. My name is Tobias Gemecke. I've spent a couple of years in Aachen to study and do my PhD. Thereafter went to IBM in the R&D department, going to the Silicon Valley thereafter to, finally come back to Europe, to IMEC first in the Netherlands and Belgium, before I was nominated full professor here at the RWTH Aachen again. My talk will cover a total of 5 different sections. We'll start about some introduction to approximate computing, and then look into Posit Arithmetic, function approximation, and time domain computing before I conclude the talk. So let's take a look at approximate computing. We can do approximation on various levels. There is apparently the possibility to do logic modification on the lower level, or change the circuitry, remove transistors, run them at a lower voltage. We can run on a higher level, where we now talk about atomic functions, for example, that realize some functionality we would like to have, but then in an approximate manner. And we can be at the algorithmic level, where also there we can apply different approximations. And at each of those levels, we can then again introduce certain knobs that adjust the way, the amount of approximation we do. Such kind of parameters can be changed dynamically, like, for example, iterations in a computational loop, or they can be fixed depending on how you realize the structure. So these are the different levels in a vertical hierarchy where approximations can be applied. On the other side, we have applications that can tolerate such approximations. So they should be in a certain degree errors resilient. Now, we don't think about banking application where we approximate what you have in your account, but maybe applications that kind of, play or produce something that is perceived by the human. So we can play with the limits of human perception. So something we don't see or hear, we can be rather imprecise on those aspects. Then there's, in today's world with the novel algorithms, there's a lot of data. We can say that data is ubiquitous, or at least we can think that it's redundant to certain degrees, right? So and then if some data is noisy, is erroneous, it doesn't matter that much. On the other side, modern applications sometimes don't really have a golden result. And if you don't have a golden result, it's a question of what is actually an error. Now, I want to bring together or bridge that from the approximation in hardware and software and the application. The question is how to do that efficiently. What we like to have, if you go in the hardware from the lower to the upper levels, is to be able to validate what we do on each and every level. So we would like to do a validation on the atomic function level. However, it's sometimes not very clear of how that relates to the actual quality of service that we then want to achieve in a specific application. For that, there's a large variety of ways to kind of express the accuracy on those different levels, but the dependency, that is not trivial. So we need metrics, and getting those metrics is not easy. We can try to kind of order that whole space of metrics proposed in literature somewhat to think about that applications have different needs. If you think about data processing, classic filtering, or maybe compression, the data is not changed or not so much different from beginning to end of the processing chain. Now, in those cases, we can nicely compare numerically the equivalence. Well, for example, if you have compression, if it's now lossless or loss-C compression. On the other side, we can use the, again, human perception to tolerate certain variations in the signal that we pass through. And then there's the other domain of application that make use of the data. They extract something, some meta information. They do feature extraction. Now here we then talk, for example, about classification, ordering, or selection. Certainly we can talk about right and wrong if you do a classification, whether this is a dog or a cat. However, if you then go to more general terms, like, for example, the sequence might not be that apparent. If you do a search, which is the best hit? That is not trivial to say. And then a slight change in the sequence might be very well tolerated. Or we have the precision. We want to kind of detect the shape of something, how close the boundary is approximated. That's, again, it's already in the word. There's approximation happening, and we have some tolerance for errors there. So let's take a look at what techniques we use when doing approximation. Well, and evaluate those. Now, the error occurrence is important. So it could be that the errors happen, once in a while. They happen stochastically, so it's non-deterministic. We can't predict of how our approximation will affect the data. On the other side, we can have deterministic approximations where we can pre-compute. With that data, we'll always get the same error or the same correct result. The degradation thereby can happen either we have a switch to turn on approximation or no approximation. We can have then an error rate, how often an error happens, or it can happen gradually. Right? So we have maybe frequent errors, but they might not be that bad. So we have this graceful degradation. The more approximation we add, the more inaccurate the result will be. It can be catastrophic, completely wrong result, like the MSB bit flip, or we can think about ways to do a bounded degradation, so we can know that the error is within a certain interval. We already spoke about the different levels that we can apply those approximation to, and then the level of evaluation, whether to do that on the atomic level or on the application level. So that's kind of a little bit of classification where to apply the techniques and the metrics to, maybe sort a little bit through the many proposals out there in the approximations. We have well-known techniques done over many years, and that's the classic quantization, right? Where we have fixed point in this signal processing, trying to minimize the number of bits, which again happens now for machine learning, where in the artificial neural networks, you try to reduce the number representation, the number of bits used there. So then block floating point is one step to have a better dynamic range, but we apply the same exponent for a whole vector, or then the floating point representation. Like I said, we tweaked fixed points in classic DSP in many 50, 60 years now, but we have now in the machine learning domain also the idea to use floating points. We like the dynamic range, but we know we don't need maybe 32-bit, less is okay, like 16-bit here, half precision. And then we figured out that sometimes dynamic range is more important than having many digits, to have less linear range, but more this logarithmic or exponential range if you want. And then the different ways that to change the exponent going from IEEE floating point, that was what has happened in the past. And there's now also the proposal to change dynamically the setting depending on your data you have. And this is a beautiful introduction to our first domain of posits, right? You can now question, is floating point really the best way of represent your data? So what does posit do? Well, it is similar in a certain extent to classic floating point. We also have an exponent and a significant, but on top there's a regime, which gives you in a much coarser grain a range where you want to be more precise than, or apply your exponent and significant to have fine-grained steps. So that's one part of the posits, but there's more ideas to that. There's the idea that there's a certain range of numbers that you want to have more precise, and that's, if you have normalized numbers, it might very well be around the value 1, that you have a higher precision around that one, and you loosen your precision the wider you go away to large numbers and to very small numbers. This happens to a certain degree already with the floating point numbers, but here with that regime, we have an additional scaling factor that allows us to go even further. So how does that look? Well, if you have now here compared the decimal accuracy for floating point, which is in green, and then in purple, we have the posits. What you can see is that for this main range of floats, you have the zigzag, that's due to the logarithmic scale we have here. Now, over the log x represented here, we see that the floats go to a wide dynamic range, but then there's a hard cutoff for large numbers. On the low side, we have the d-normal numbers, which give such a gradual reduction in decimal accuracy, but it goes further there. Now, what do the posits do? They provide high accuracy in the central range, which is potentially more important for specific application. And then it goes in a much wider dynamic range, allowing us to cover with less bits, a wider range, which can be sufficient for certain applications. The one aspect that we have for floats, and which is not well defined, is the case when we merge operations together. And so if you have a multiply, accumulate, this could be done in a single step to avoid rounding errors. That's already predefined in posits, and that's kind of the quire here that then allows to do a multiply accumulate operation, for example, in full precision. Now, this is just how data and decimal accuracy looks like. Let's take a look at a specific function. What we have here, and Gustafsson has looked at various of those unary functions, showing that, looking at different data here on the x-axis sorted by the loss you have, and you show the loss, you see that there's, for both cases, a certain number of possible representation that have a very small loss, but then floats go for a much wider, for a much larger set of numbers, high, with a very high loss, which is much less for the posits. So indicating that posits have the capability of providing far less loss for the many representations they can provide. Here is the example of an 8-bit number. So in general, that led Gustafsson to the statement that with a 32-bit posit number, you can safely replace a 60-bit floating point number, at least for quite a number of applications. Now, not only that, but posits are also more robust, they are more reliable. What we show here on this plot is the impact of having double-bit errors distributed anywhere in a 32-bit representation, float or posit, and then again looking at what happens if you have those bit flips. You can see that those bit flips leads to a much higher mean relative error in the floating point, which is in blue here, as compared to the posit numbers. Now, why is that? How can the posit be having more dynamic range, being more precise, and still having less impact by those bit flips? Now, that has to do with the way the posits are represented. And it's a little bit tricky to understand, but let me try to explain that rather quickly. Right? We have that regime which gives you really a big scaling factor up front, like the 4096, 256, and then 16, 1. These are the regime multipliers you have. Now, they need a lot of bits, and that's the way how it is encoded. If you go for large multipliers, very small or very large numbers. The main range, where you have a lot of representations, binary representations of numbers, you can see that the regime is rather small, right? So the probability of hitting with a bit flip, the regime bits, is small. That is, a bit hit has a small impact on the total accuracy. What happens on the other side is that you get more bits then to represent your significand in that central range, right? And hitting the significand only has a small change. It only introduces a small error as compared to hit the exponent, like there's more exponent bits in the floating point number in the many cases, especially around 1. So posits, yeah, they seem to be a very interesting options to do approximations. Well, maybe they are even more precise, or they could be used to run with less bits. A key topic in approximations, trying to do with less bits. Quantization is getting you less quality. Posits maybe can preserve you even the quality. Going one step further into approximation, we said we want to also approximate functions. We have taken here the example of transcendental function, the sigmoids and the tangents hyperbolicus. Baseline is 32-bit floating point, and we looked for a low-cost PWL, a piecewise linear approximation that can nicely be done with those linear segments here. And the beauty is that the endpoints of those linear segments can also be very well defined as power of 2s. So what you see here, a somewhat complicated equation for sigmoid, is basically here. It's 1 over 2 to the power of something. That is basically a shift. And here's another shifter of the fractional part of the actual number. Now, this is not division, this is just shifting. So you can also write that as a binary string, where you see here is just the fractional bits, and here is a number of, sign or non-sign inverted bits, depending on the integer value. So it's very simple to compute that and realize that actual function. And once you have sigmoid, apparently 10H is also simple to derive. We talk so about the simple structure, something to do with the sign that you do. You have a shift operation, some conversion logic that is very primitive, mainly in kind of an adder circuitry that computes the shift amount. Now, how well does that work? So that's what's shown here in the case of Amnes. We try to preserve an accuracy of 99% and then use different ways to approximate the 10H function. What you can see is that here in many cases, even having a low error, it doesn't help, right? It's still noisy, distributed around that accuracy level. Now, what you see is only here to the very right that then suddenly points are divergent. So here it's an area where it is apparently not accurate enough. But here still in this range, it's similar to the very left-hand side. So errors don't contribute that much. It's somewhat the noise level you have that creates this going above and below this 99% level. And here very well, you see 2 points at the lower bound even that are done with that piecewise linear. Now, that is very basic. One could add some correction and try to be as accurate as well as binary brain float 16, right? You can do that, but does it help? Is it good for even more complex networks? So we took the example of the Libre speech recognition task, which is quite, a difficult task. So you have many hours, you have different speakers, female, male, nice to understand, clean voice, other, which are more hard to decipher. And then we use 2 networks. The one is a recurrent neural network transducer, RNNT network or model. And then we have an attention-based encoder, decoder, and AED structure. You can see here that the word error rate is reduced if you train longer and longer. And here we talk about days of training, right? That shows how complicated those cases are. As said, we want to apply the simple technique we mentioned before, and we just do that after training. We don't no retraining. It's just an in-place replacement, right? Very straightforward. We look at the word error rate. Now, looking at the RNNT model first, we can see that the reference floating point 32-bit is giving us a certain word error rate. Now, if you reduce that to 16-bit, there's virtually no change. That's kind of more or less in the noise. Sometimes it's even better. We can see that this primitive piecewise linear function, it has a reduction. We can see that, but it's not that bad. It's not catastrophic. If we correct it further to get to bfloat 16, we see it gets better, but it doesn't achieve bfloat 16, right? And we see a similar trend for the other decoder. Now, why is PWL plus not achieving bfloat 16 accuracy? Well, it's simply because we only tried to fit between plus and minus 3.5. It didn't go any further because then it's almost saturated. But I mean, that's a little gap where if you would extend this modeling approach, we could, I mean, apparently get back to full bfloat 16 accuracy. With that, let's do a next step. I mean, we still want to be discrete, like we said, but we now, I mean, go into the domain that is almost analog computing. Well, it's time domain computing, which can be somewhat seen situated between discrete computing and analog computing. Well, it's analog as much as it's not synchronized, it's continuous in time, but we can still make sure to compute in discrete time steps, which is this delay element. So what you have is multiply accumulate. You have an XOR gate, it's a binary neural network that then selects the multiplexer, and either we have a discrete delay step added or not. So what happens in such a binary neural networks? You have lots of mag ops here apparently, but then the binary neural network is just an XOR operation plus the pop count function. Now, being discrete means we have low variation due to process voltage whatsoever, and the tau between or for those delay steps is large enough that we can operate completely error-free. However, this is apparently not the most efficient way of doing that. If you scale voltage or make the delay smaller, we get those distributions to kind of overlap, and then we are no longer error-free. One can show that as a trend. Well, you have the sigma over mu as a function of voltage. You scale the voltage, you see the sigma over mu goes up. And you can also do that at the same time changing the delay elements. And then looking at the mean squared error, you see how those go up correspondingly with the sigma over mu as expected. Now, why would you do that? Well, performance goes up for smaller tau, energy efficiency goes up for smaller tau as you reduce the caps that increase the delay or make up the delay, or also because you have smaller gates which have more process spread in there inherently, or you scale voltage. All of that will improve the energy efficiency, and then on the other side, increase the mean squared error. So how bad is that? Now, looking at that sigma over mu, you see that the error probability steeply increases even for small levels of sigma over mu. However, if you look at that network, we have the convolutional layer, and thereafter comes a pooling layer. In this network, we have max pooling, so we only pick the largest value, and due to that, a lot of errors don't occur at the output. So we have a much slower increase in error probability. So if you now look at the accuracy of our network, what can we see? So that's the blue curve, that is the test accuracy. We are above 99% with the binary network, and it has a low impact at the beginning, and then we see the steep decline if the error of sigma over mu gets too large. What we can do is we can train our network upfront with random noise just to make it more robust against inaccurate inputs. We can see that at the beginning it's a little worse, but it stays at a higher level, which is nice, and we can extend to higher sigma over mu levels and have a not so strong degradation in the test accuracy. With that, I'd like to conclude my presentation. We have seen challenges. One aspect is the need for generic solution to be able to apply that to many different examples, which is not trivial. Many of those approximate computing samples are very specific to one application. On the other side, we discussed the problem of doing optimization on the lower levels, looking at atomic functions, and then having an unclear relationship to the quality of service on the application level. On the other side, we looked at various interesting ideas that can move this domain further forward, providing discrete and, well, at the end, it was non-discrete anymore, non-deterministic noise, which provide this gradual trade-off in a nice way. And these domains were Posit Arithmetic, function approximation, and time domain computing. Apparently here at the conference, you can find many more examples in this domain. Thank you for your attention. If you have any question, please, you can also email at info@ids.rw-aachen.de. Thank you.